In standard RAG pipelines, the first step is always the same. Take a heavily structured document and shatter it into fixed-size, identical chunks of text. Slicing a document into rigid windows forces you to sever its semantic continuity. The essential section headers, footnotes, and surrounding paragraphs that give a specific sentence its actual meaning are completely stripped away. Embedding models then take those context-stripped chunks and compress them into fixed-length arrays of numbers, plotting them as individual vectors in a high-dimensional mathematical space. When a user submits a prompt, the system embeds the query as a central point, relying on mathematical proximity to pull back the nearest neighbors. Known as top K similarity search, it sets a hard boundary, capturing only closest dots and ignoring the rest. At an enterprise scale, this architecture degrades. Retrieving a mathematically proximate chunk without the structural context of the original document results in silent information loss. In professional domains like law or medicine, there is a strict operational difference between two text blocks being mathematically similar and a block actually being relevant to a question. The first failure mode of top K retrieval occurs when the system returns results that look highly similar to the embedding model, but provide the wrong factual answer. Two identically structured text blocks, one establishing liability, the other denying it, are plotted as the exact same vector point. The second failure mode requires logic. The genuinely relevant, differently phrased chunk falls far outside the search radius. Because basic vector search lacks a mechanism for reasoning over a document structure, this highly relevant information falls past rank K. It disappears entirely. You never get an error message, you just get a worse answer. Mathematical proximity is a flawed proxy for logical reasoning. To fully eliminate these retrieval gaps at an enterprise scale, the architecture needs a reliable way to navigate a document's internal structure directly. The alternative is a vectorless RAG architecture. Instead of chopping text into disconnected embeddings, this framework maps documents as intact, hierarchical structures. This diagram illustrates the transformation. A single document is mapped into a strict hierarchical tree, nesting sections, pages, and content blocks. To retrieve information, an LLM evaluates each node, making a yes or no decision to open a subtree based on the query. Because the LLM navigates the original structure of the text, it preserves full semantic context at every step, bypassing arbitrary top K cutoff limits. This works flawlessly for a single report. The bottleneck emerges when you attempt to run this contextual tree navigation across millions of unstructured enterprise files. Hexadecimal file system is technically a tree. Folders contain subfolders, which contain files. But in practice, enterprise document management systems and S3 buckets operate as entirely flat data lakes. Even when a rigid folder hierarchy exists, files are often sorted into directories labeled MISC or legacy. These labels provide zero semantic signal for an LLM's routing logic. Pointing an LLM at a million-document corpus and asking it to navigate a static, one-dimensional folder hierarchy is computationally unviable. The model gets pruned in the wrong direction and fails to find the target. To bypass this limitation, the PageIndex file system introduces a structural mechanism for unstructured data, synthesizing a semantic hierarchy over the corpus where none existed. This diagram demonstrates a flat enterprise data lake. The system extracts LLM-inferred metadata, identifying categories like vendors, regions, and dates. These tags generate virtual nodes, assembling into synthesized parent layers. A single contract can now simultaneously connect to multiple nodes, breaking one-dimensional constraints. A standard flat file system forces a document into a single rigid folder path, strictly limiting its discoverability to one axis. By injecting LLM-inferred virtual nodes, the system creates a multi-dimensional hierarchy. This provides the specific semantic signals an LLM requires to prune irrelevant branches early. However, locking these virtual nodes into a fixed layout assumes every search follows the same logic. No single static hierarchy can efficiently answer every possible question. This requires a mechanism called query-dependent trees, where the internal nodes of the file system are assembled strictly on demand. This visualization shows one dataset split across two screens. Depending on the query, the system dynamically organizes the documents. A search for vendor charges builds a vendor-then-year hierarchy. A search for renewals instantly shifts the layout to status, then date. The architecture executes this rapid restructuring precisely at query time, without requiring the system to re-ingest or re-embed a single piece of data. Query-dependent trees allow the file system to shapeshift. They provide an optimized, single-use traversal path tailored specifically to the logic of the immediate prompt. Even with dynamic trees, one computational bottleneck remains. Forcing an LLM to evaluate deep, uninformative folder layers wastes massive amounts of compute and time. This graphic shows the default layer-wise traversal strategy. When virtual nodes possess highly informative semantic labels, the LLM carefully evaluates and descends through the structure one layer at a time. But when the LLM encounters uninformative legacy directories like folder 1, stepping layer by layer is useless. The system solves this via dynamic flattening. When an unhelpful node is detected, its entire tree instantly collapses, bypassing the intermediate steps entirely. This defers the discrimination logic directly to the actual content leaves at the bottom of the tree, avoiding wasted evaluations on useless folder titles. By rapidly alternating between layer-wise traversal and recursive flattening, tree search remains efficient even when scaled to millions of documents. We can now track the complete execution pipeline. The system takes a flat data lake, synthesizes a dynamic tree tailored to the prompt, and targets an LLM to navigate the exact structure it built. The retrieval process functions as a highly optimized search path, reading structural labels, dynamically flattening unhelpful branches, and cutting directly to the relevant evidence. This architecture produces a fully readable, auditable route plotted over a 1,000,000-document tree, leading from the root to the leaf. Users can explicitly trace this path to verify exactly which sections were opened, skipped, and why the evidence was selected. This level of transparent evidence tracking is impossible with the black box nature of standard top-K vector retrieval, which returns isolated chunks with zero contextual history. Vectorless tree search restores explicit, contextual reasoning to enterprise architecture. By navigating the document tree instead of measuring vector distance, the system ensures that relevance is determined by the content's logic, even with